So we're going to start off our second morning session with a talk by Marina Kounkel, who is going to talk about kinematic identification of stellar groups and association with coherent ages. Hello? Hello? And here's the slide.
Okay, thank you. All right, today I wanted to continue the topic that Melissa has brought up and talk a bit more about star clusters and moving groups. And to begin with, what are star clusters? What is the first thing that comes to mind when you hear that term? Do you perhaps think of a globular cluster, which is a reddish blob that is full of the that has a spherical distribution of stars, that is a remnant of the first epoch of star formation in the galaxy? Do you perhaps think of an open cluster, which is full of massive blue stars that are just waiting to die off? Or do you perhaps think of a young embedded cluster that is sometimes grouped together with open clusters, sometimes not, but it's full of stars, full of gas that's forming yet more stars, full of nebulosity and dust lanes? These clusters are great to help us determine the ages for the stars. For a random field stars, you normally wouldn't necessarily be able to tell a precise age of that star, even with some of the more advanced techniques. But within the cluster, all the stars have formed at the same time, so it is possible to tell an age of their aggregate. So when we look at the HR diagram for these clusters, we see that in the youngest age range, we see that in the youngest age range, we have a sizable pre-main sequence component. Then after a while, all the stars enter the main sequence. And then after the cluster evolves even further, higher mass stars begin to die off, and you have a very clearly defined turnoff. So by modeling the cluster sequence, you can tell what is the age of these clusters. The difference between open and globular clusters isn't just their age, isn't just their morphology, it's also the spatial distribution in the galaxy. The globular clusters tend to be distributed spherically around the galactic center. And there's, of the latest census, there's around 200 of them known. On the other hand, open clusters and young clusters as well tend to be distributed along the galactic plane. And as of the latest census, there's more than 2,000 of them. So significantly more open clusters are known than globular clusters, and their census continues to grow every day almost. How does one find an open cluster or cluster in general? I will give you all a minute. Here it is. That was fairly easy. In the olden days, this is pretty much how we've always would search for these clusters. We would look for overdensity of stars in a particular region of space. Now, a lot of stars in this field, there aren't necessarily cluster members. There's a lot of field stars that have nothing to do with it. But if you're lucky, if you look at the color magnitude diagram, you would have a cleanly defined isochrone, and you might try to isolate stars along this isochrone to try to select the probable cluster members. This method is still prone to quite a bit of contamination, but nowadays we are much luckier because with Gaia, we have information on the proper motions of stars as well as their distances. And clusters aren't just an overdensities of stars in the plane of the sky. All the stars within the cluster are also moving together, so you can see a very clean overdensity in the proper motions. And you can also see the excess of them at a particular distance. So just by selecting stars in the proper motion plane, we can have a relatively clean sample of the likely members, where we have a very cleanly defined isochrone together with a binary sequence and some blue stragglers as well. And nowadays, the cluster doesn't even have to look like this for us to be able to identify it. It can look something like this. That is to say, when you're looking at it, at the distribution of stars with your eyes, you may not necessarily even see the enhancement in density. But because we do have so much information with Gaia about the proper motions and parallaxes, we can find more diffuse clusters of stars, even at this density. That is to say, the number of stars that is necessary for detection has went down significantly in comparison to how it was before Gaia. But now that we do have Gaia, we need to have a more automated ways of searching for them, because we cannot look at just the images of the sky anymore. And one of the techniques that people are utilizing to search for these structures is called hierarchical clustering. And how it works is, first of all, you take a set of stars and you measure distance between every single star to every single other star. Now, I say distance, I don't necessarily mean a spatial distance. Distance can be whatever you want it to be. You can throw in predictions of the sky, parallaxes, proper motions, anything else, radial velocities if you have them. And then using these distances, you will construct a minimum spanning tree. That is to say, you will find the first shortest distance that will connect two stars, then the second shortest distance that will connect a previously unconnected star, the third shortest, the fourth shortest, and so on and so forth, until all the stars are connected in this diagram. Then you'll need to find appropriate places to cut the branches of this tree. You will need to find a place where you would have the cluster set of clusters that are neither too large nor too small. That is to say, you don't want to group all the stars together, because then you would have contamination from the field stars, but you don't really want to miss any of the obvious members as well. So sometimes it's a bit of a fine-tuning game in terms of what would be the appropriate size at which you cut. And there are a number of algorithms that are currently available that perform this type of operations. One of them is dbScan or HDBScan. There are some of the others that approach clustering a bit differently using slightly different technique, for example, but it's important to keep in mind that what these clustering algorithms do fundamentally is they search for structure in your data set. This can be applied not only to star clusters, but it can be applied to any sort of process where you're trying to identify structure in the data. And even so, if you have a similar data set and you apply different clustering algorithms onto it, and you might end up with a different number of clusters, you would have a slightly different number of stars in these clusters, you're still tracing the same structure that is underlying. It doesn't necessarily mean that a different clustering algorithm gives you something different. And through applying these algorithms, there has been a Gaia revolution in terms of searching for new open clusters. There has been easily a dozen of papers out there, each identifying hundreds of new clusters. For example, this is an example of one of them, where you're looking at the galaxy top down with the sun at the center. Galactic center is to the right. The red background are the previously known open clusters. The black dots are newly discovered clusters in this paper. So this particular paper has found quite a large census of them outside of 1 kiloparsec. And again, there have been dozens of papers, and sometimes it can actually be a bit difficult to keep track which discovery belongs to whom, because sometimes you can't necessarily cross-match them very easily. But with an increased census of them, perhaps it comes time to evaluate some of the things that we always took for granted. It is often said that most stars form in clusters, but these clusters tend to be fairly short-lived, that only half of them will make it to the age of 10 million years, and only a small fraction, something like 5%, will survive to the age of 100 million years. And when you hear something like that, it's impossible not to bring your own assumptions about, first of all, what is a cluster? How big is it? How massive? What's its morphology? And again, what does it mean to survive, for clusters to survive? How does it disperse? Over what timescales? And chances are the assumptions that you would have hearing these words would not necessarily be the same assumptions that have been made when these terms have been coined in this seminal review paper that everyone always cites. Back then, they defined a cluster as something that contains 35 stars within some sort of density threshold. So it was actually a fairly permissive set of criteria that would include most of the stars that people would call clusters. But nowadays that we can push even further with Gaia, perhaps it's time to reevaluate this set of criteria. And there has been actually a recent paper that updated the statistics. They said that 16% of stars are born in bound clusters. In some ways, it's better because nowadays you actually take advantage of the full census of them. But in some ways, it's worse because now you're bringing in the concept of boundness to them. And boundness is really, really difficult to measure for a vast majority of clusters. And there are actually quite a bit of a debate about which clusters are bound and which ones aren't. And with this in mind, more and more I find myself questioning, well, what is actually a star cluster? How do you properly define it without having any sort of arbitrary definition? And more I find myself thinking that I don't really have a definition of a star cluster. And indeed, if you ask pretty much anyone who has worked on clusters with Gaia, searching for them, you will get a range of answers. And that range would be somewhere from a wiggly hand gesture to incoherent screaming. And it's not as much of a joke as you think it is. And at the heart of it kind of lies a rather binary way of thinking, that we tend to think of clusters as that is something that is compact, something that is isolated, something that doesn't have anything else outside of it. So we tend to think that a star is either inside a cluster or it isn't. And a real world situation is much more complicated, particularly if you approach it from the point of view of star formation. For example, let's take a look at one of the closest region of the ongoing massive cluster star formation, the Orion complex. And as that list of euphemisms suggests, it does have quite a few clusters, one of which in particular is the Orion Nebula. It is a singularly most massive cluster that we have in the solar neighborhood. But when we zoom into it, well, it actually does have quite a bit of substructure. That you do have a central overdensity corresponding to the trapezium found at the heart of the Orion Nebula, but you do have a separate overdensity corresponding to the B and KL Nebula. And you have a more compact core surrounded by more diffuse halo. And protruding away from that cluster, you have a filament that is still actively forming stars. Well, I mean, this cluster is very young. It has an age of around 2 million years, and it still has a lot of molecular gas. And when we zoom in onto that filament, well, it looks very clumpy. There is a lot of substructure in there. That you have these hubs of star formation. And sure, you wouldn't necessarily call them clusters in their own right because they're all part of the Orion Nebula. But what if these hubs were found in a different star forming regions? You might be tempted to call these clusters. And once you start counting these hubs, well, we can be here all day, because when we look at the rest of the molecular cloud, which contains the Orion Nebula, as you can see, star formation is a very clumpy process. Star formation is a hierarchical process. You are forming structure on all scales. And you can continue to subdivide this region into smaller and smaller groups until the word cluster loses all its meaning. I have seen it applied to as few as 3 stars. Or you can go the other way. You can look for the largest meaningful structure that you can trace out. And in this case, this largest structure would be the rest of the Orion complex. And it is a very large structure. It fills out the entire constellation of Orion, literally from head to toe. Here's the belt, if you're more familiar with that feature. In physical units, it spans over 150 degrees, 150 parsecs, and it has been continuously forming stars for the last 10 million years. It is an extremely massive structure containing over 10,000 stars as of the latest census. And sure, a sizable chunk of those stars are found within the Orion Nebula, but certainly it is a massive structure in its own right. And if you look carefully at it, you might pay attention to the proper motions of the stars pointed to these vectors, and you'll note that the entire structure is expanding. There's an expansion happening at the top of the region, right over here, away from the central point, and it's happening in this region away from this point. And the expansion is such that you can actually trace the bulk of these stars back to the central point with a similar age of around 6 million years. And even so, this region looks like a single population in the plane of the sky. If we were to twist it and look at it from sideways, you can actually see that it is broken down into multiple components. And the region that is closer to us, Orion D, is moving towards us. And the region that is further away from us, Orion C, is moving away from us. And they would have met somewhere in the middle with a similar age of around 6 million years. And even the Orion Nebula, it also has velocities pointed away from the center of the bubble. So you do actually have a three-dimensional bubble surrounding of stars surrounding some sort of space. So what probably has happened is there used to be a supernova there. Originally, back in the day, Orion complex might have been a simple, boring filament of gas. It started forming stars some time ago. One of those stars that it has formed has died off. It created a supernova. That supernova created a shockwave that has propagated through the gas. The gas quickly got swept away, triggering the formation of the next generation of stars, quickly consuming the gas, forming Orion C and D. But the part of the shockwave that got traveled into the filament continued seeping along more and more and more gas, eventually accumulating enough material to enable the formation of cluster as massive as this. And indeed, we can actually see the signature of it within the Orion Nebula itself. That normally when we think of clusters, we tend to think of them as all the stars are found on the same distance, give or take a few parsecs. But because Orion Nebula is so young, we can actually get ages for the individual stars. And when we separate them out into different layers, we can see that older stars are actually found at a slightly different distance of around 385 parsecs. And the younger stars are found slightly further away at a distance of around 395 parsecs. So 10 parsec separation is very significant because the cluster in the plane of sky is only 2 parsecs long. So this is quite a lot. And going back to this picture, what this means is that the older stars are found inside the bubble, and the younger stars are found deeper within the filament. So you can actually see the star forming front being pushed through the cloud. So this is just to give an example of the complexities that are involved in star formation, that you have many different processes that influence the structure that you end up forming. But it's also worth keeping in mind, even so that we do have a significant expansion signature, the velocity dispersion across the entire complex is just 4 kilometers per second. It's significant, but it is fundamentally much smaller than the velocity dispersion of the field stars. And this is actually kind of on the larger end of what you would find in star forming regions. So given that Orion complex contains 10,000 stars, how long will it take for all of the stars to fully disperse? How long will it take for all of them to lose any information on the initial velocity structure with which they formed? How long will it take for us to take a look at this region of the sky and no longer be able to see a massive structure that was once forming there? Would it be another 10 million years, 20, 50, 100? And as it's interesting as Orion complex is, it's far from being the only one. There are plenty of other star forming regions. All of them tend to be fairly massive, containing at least a few hundred stars, if not a few thousand stars. All of them tend to be fairly dynamically cold, even much colder than Orion. That is to say, they have even smaller velocity dispersion. So how long will it take for these structures to disperse? And by that in mind, if we were to take a look at 10, 20, 50, 100 million old open clusters, should we expect them to be isolated? Or should we expect to find them alongside a moving group that was once forming alongside them in these extended structures? Well, the idea of finding moving groups isn't entirely new. There have been approximately a dozen of them known within a volume space of around 100 parsecs. Very few of them have been known beyond that. For fairly good reason. In order to find moving groups, you need to have information on stellar kinematics. And the best source of stellar kinematics until recently was Hipparchus. Hipparchus didn't have much sensitivity or resolution to push beyond 100 parsecs. So you might try a bit, but this resolution degraded severely. But now with Gaia, we can push it by an order of magnitude, maybe more. And so with this in mind, it is possible to perform hierarchical clustering similar to the ones I showed earlier to try to identify all the structures that you can in the Gaia set. In total, we've been able to identify more than 8,000 different moving groups within 3 kiloparsecs. And these moving groups consist of almost 1 million stars. So here, these stars are shown in blue, and in contrast, in yellow, you see the previously known open clusters within the same volume of space. So you can see there's quite a significant difference in terms of spatial coverage. And the nice thing about moving groups, just like with clusters, presumably all of them have formed at the same time. So it is possible to determine their age through isochron fitting. And for the most part, they do follow quite nice set of isochrons, where you have the youngest groups in red, still having sizable pre-main sequence population that eventually drops down onto the main sequence. And then the high mass starts to begin to die off as you get ages beyond 100 million in purple. So this, by default, currently becomes the largest census of stars with known ages. And for the most part, we do know them within about 10% level. And we can take a look at where all these stars are located in the sky as a function of age. And this is just one projection that we can get with Gaia. We can take a look at all the components of motion, not just the position on the sky, the top panel, but also the position as a function of parallax, second panel, or the last 3 panels show various velocity components. And this is very busy. So let's take a look at just the youngest stars for the time being. Here we're looking at everything younger than 30 million years. And what becomes apparent, particularly looking at a middle plot, is that different populations have different peculiar velocities relative to one another. That is obvious enough. But an individual population can remain coherent for several dozen degrees in the plane of the sky, or in physical units, something on the order of 200 parsecs. And these strengths remain consistent in all of the dimensions, not just the velocities, but also position. So these structures are filamentary in their morphology. And even you can see that in radial velocities. Now, these radial velocities are from Gaia. Gaia in general doesn't have greatest radial velocities for the pre-main sequence stars because they're very active. But even there, if you're careful about selecting a sample, you do see the same smooth coherence. Now, it's easy enough to look at the youngest stars, but we were to look at something a bit older, something on the order of 1 giga-year. Well, this is much messier, but with some careful poking and crawling at the data, it's possible to find these string of stars even at these fairly advanced ages. And separating the sample into these extended strings and the more compact cluster-like groups that don't have extended halos around them, we can see that looking at them as a function of age, strings tend to be ubiquitous at the youngest ages. Almost every young star that's formed up to 100 million years is found in these extended strings. On the other hand, these isolated cluster-like groups don't really come into prominence until around 300 million years. And looking at it in a slightly different way, we can take a look at the number of stars in each population as a function of age. And you find that at the youngest ages, you can have whatever number of stars you want to have. You can have a few hundred stars, you can have several thousands of stars. But at the oldest ages, it's rare to have more than a few dozens of stars that are still clusterable together. And most likely, the stars that end up over here have been originally some of the most massive ones to begin with, for them to still have any sort of coherence at the older ages. And that isn't to say that these groups aren't expanding. Here, for example, here is an example of Theia 456, where using the Gaia proper motions and various radial velocity survey data, it was possible to try to trace it back to how it would have looked 60 million years ago. And right now it is 190 parsecs in diameter. 60 million years ago, it was 120 parsecs in diameter. So it has expanded quite a bit. But back then, it still had the same perfilamentary morphology it has right now. So with that in mind, what is the origin of this extended structure? Well, it's unlikely to be caused solely due to the tidal stretching of the previously compact clusters. Because otherwise you would expect everything to start very compact and then stretch out. And you see the extended structure be very dominant even at the youngest ages. And more importantly, sometimes you don't even have a classical cluster at the center of these strings. You might have a cluster, like you have Orion Nebula within the Orion complex, but it is not at all a requirement. Rather, it's likely that the structure is primordial, that we know that stars from molecular clouds tend to be filamentary. It stands to reason that any time that you you have gas, you're going to start forming. So they're going to inherit the same morphology as the molecular clouds themselves. They are slowly dissolving over time. Eventually, only the densest and most cluster-like parts will remain, but some of the most massive ones will be able to survive for a little while longer. And switching the perspective a bit about how we're looking at them, before we were looking at them in the projected plane of the sky, now we're looking at the galaxy top down. The sun is at the center, galactic center is to the right. And here we have various spiral arms that we have in the galaxy. Here we have the local arm. This is a Sagittarius arm. This is a Perseus arm. Sagittarius, yes, Sagittarius. And here all the strings are traced along their spines, and we're looking at just populations younger than 50 million years. And as you can see, their orientation isn't precisely random, that they are very closely associated with the molecular arms, oriented perpendicular to the arm in parallel to one another. And talking with people who study other galaxies, looking at the high resolution maps of molecular gas, well, people find that when you have the spiral arm, there are often these feathers of gas protruding away from the spiral arms. And again, when you have gas, you're going to start forming stars. It is reasonable to assume that these strings might have formed from these feathers. And since strings are ubiquitous among the young stars in the solar neighborhood, we can assume that this may be the dominant mode of star formation in our own solar neighborhood. And before we were looking at just the youngest populations, we can also look at the populations that are a bit older than that. And I won't go into too much detail, but it's very interesting to see how the morphology of the galaxy that we're tracing at these ages differs from the youngest age range. For example, they no longer follow the spiral arms cleanly. For example, here we have a void of the older stars in this region. So this is something just to keep in mind, that the galaxy is a very dynamical space, and it is evolving over time as well. But as great as all of these clustering techniques are, you would never be able to identify every single star that have originally formed within a particular moving group. Some stars are very eager to leave their nests, and some do it much more violently than others. Even in the youngest regions like Orion, you have plenty of stars that have already escaped their confines of the star forming region. Because they have different kinematics, you cannot identify them through using the clustering on the kinematics. So what some of the reasons, some of the other ways we can use to search for these stars? Well, some of the examples is chemistry, like Melissa has shown us earlier. There are a few others. For example, as long as you're dealing with the pre-main sequence stars, you can carefully select a parameter space of low mass young stars that is very clearly separate from the main sequence and the binary sequences. And you also separate them from the red giant branch. And so it is possible to create a rather clean sample of these pre-main sequence stars. A different way that you might be able to select them is through gyrochronology. So the pre-main sequence ages work up to the age of around few tens of millions of years. Gyrochronology in principle could work up to the ages of around a giga-year, maybe even older. And how gyrochronology works is if you have a rotational period of a star from surveys such as TESS or potentially Gaia, you can see that the young stars tend to have rotational periods that are very fast, but as the stars age, rotational periods slow down. Now, gyrochronology isn't quite a mature enough a technique to be applied indiscriminately towards all fuel stars. It has quite a lot of success when you apply it to individual clusters. But perhaps in maybe another 5-10 years, we would be able to calibrate it in such a way where if we have a sample of rotational periods of all stars across the sky, we might be able to estimate their ages through gyrochronology. But for the time being, we can see what is the sky looks like when we're selecting out just the pre-main sequence stars, for example. And here we're looking at the stars that are younger than around 2 million years. We have various populations such as Orion, Ophiuchus, Taurus, Perseus. And this isn't quite everything, but this is a solid 80 to 90% of everything we have known about star formation until the last 10 years or so. So if in the past, if you were to ask anyone to talk about star forming regions, they will name one of these regions. Here we're looking at the populations that have ages 2 to 5 million years, and we're starting to fill up some of these regions. A few others show up in the play. 5 to 10 million years. Vela is starting to show up. Vela has been virtually unheard of until the last 10, 15 years, but nowadays it's starting to become quite a popular star forming region. Here we have Cepheus. Cepheus is a big mess that is very hard to disentangle. So people have been a bit shy about getting into it. 10 to 16 million years, 16 to 25 million years, and finally at the ages of 25 to around 40 million years. And this is basically Terra Incognita, because these stars, they're too old to have been really analyzed in any detail by the star formation community, but they haven't also really been analyzed by the people who study clusters because they are too diffuse. But nonetheless, many with clustering, it is possible to pick out many of these parts that are still co-moving. But of course, you wouldn't be able to pick out every single star. So to bring it to a close, in the last 10 years, with Gaia in particular, and with a few other surveys, we have progressed significantly in terms of being able to estimate ages for stars. Currently, we have a census of stars that is over a million, contains over 1 million stars, for which we have some sort of age estimate. And as some of these other techniques mature, and as we get more data from spectroscopic surveys, and as we get to the point where we are starting to get rotational periods from all of the stars from all these other surveys, it is possible to increase the sample by another order of magnitude. And having ages would be very useful for a number of different disciplines, including exoplanets. Thank you.
We have time for questions. As usual, if you're a person who has a question, come to the microphone, and while we wait for
Yes. So first question, is supernova shockwave the only way that aids in star formation for clusters?
Say it again.
Is supernova shockwave the only way that aids in star formation for clusters?
Well, we don't know. We have an example of one in Orion. We are still trying to understand the kinematics of all of the other regions to figure out how they would have formed. There are a few other examples where you have several regions forming at the interfaces of various bubbles, but there are other clusters where this is not necessarily an obvious case. So we're still working on understanding how clusters form.
yeah. Take your first question.
Hi, thanks very much for that. Very interesting. I was wondering, do we know how completed the current survey of open clusters and of the associations in the galaxy with Gaia data?
How complete they are? Well, we don't know what we don't know. In some ways, Gaia has revolutionized the way that we're looking at these moving groups. We certainly wouldn't know much about the lowest mass stars in these regions. So we generally go up to the G of 18 in Gaia bands, because that's where you have good photometry, where you have good astrometry. Lower mass stars wouldn't necessarily have quite as good of a data as we have for the high mass stars. And some of the more diffuse regions, they can also be rather difficult to pick up with clustering. So I wouldn't expect there to be a ton of them, but we're still probably missing quite a few of them.
Okay, thanks. And another stupid question, maybe. Can we go back in time and extrapolate the proportions to try and trace back the clusters which have this dispersed in time?
Yeah, so this is right now the limiting factor are radial velocities. As I mentioned before, Gaia radial velocities aren't really optimal for the pre-main sequence stars because they are very active. They have a very large dispersion, even if they are RV stable in other surveys. But once we have that, we definitely can, at least with proper motions right now, we can definitely try to trace them back and try to reconstruct everything together. Right now, we're primarily doing it on the individual star forming regions, but in future, we're hoping to be able to expand it across the neighborhood as a whole.
Thank you very much.
That was an excellent talk. Thank you. My question is related to like cluster boundness and also cluster survival. So cluster boundness obviously is something that we can calculate, but survival, like you mentioned, is like very difficult to quantify in some ways. So I'm curious what your thoughts are on whether those two are related in any way, like are bound clusters more likely to survive longer or what?
Well, cluster boundness isn't that easy to measure. For example, Orion Nebula, this is the singularly most massive cluster. You would think that if it isn't bound, no other cluster would be bound. People have been debating whether Orion Nebula is bound for the last 20, 30 years. I think it is, but it does have a relative dispersion that's a bit larger than you would assume for a virial equilibrium. In general, kinematically, there's not really doesn't appear to be much of a difference in terms of dispersal time frame for the moving groups or more compact clusters. So there's probably some correlation in terms of boundness and survival, but again, they're losing stars along the way, just like any other moving group.
Thank you.
Hello, thank you for the very nice talk. In the beginning of the talk, you had talked about identifying clusters and that we began with looking at overdensities in the sky. I do not quite get how we evolved from that and where we are now in identifying clusters.
So the main step is now we have Gaia. With Gaia, if you have overdensity, not just in the plane of the sky, but you also have overdensity in all the other components of the phase space, like the position and velocity space, and you have the overdensity in proper motions. And you can separate that overdensity from the field. You no longer need to be able to notice overdensity in the plane of the sky against the background of all the other stars. So by selecting, by relating how closely the stars are aligned in the parallax and proper motion and position of the sky and radial velocities, if you have them, you will be able to identify the cluster without necessarily visual examination component.
Thank you.
I think we have time for a couple more online questions.
So next question, can any of the older clusters be traced to Enceladus merger?
I think Enceladus is a bit further away than the limits that we are placing them, and we're primarily confining ourselves to the galactic plane because that's where the open clusters are forming. Enceladus is mostly in the halo. Maybe in principle, in the future data releases, it may be possible to extend the cluster into those distances.
Next question. Your work focuses on identifying coeval associations, but is there much research on the dynamic side of the likelihood of chance small to medium associations, things that are co-moving and physically nearby but did not form together?
Well, by doing everything at once, or just trying to identify every single thing that we can find in the solar neighborhood, we are able to identify the groups that are kind of nearby and may not necessarily form together. But in some respects, if they are nearby, There may be a question of how precisely they might have influenced each other in terms of their formations. So there may not necessarily always be completely generalized.
All right, we still have time for more questions if there are more, but those of you who have poster props coming up next, if you start coming down and lining up. Do we have more online questions?
Yes, we do. So this question asks, why are globular clusters found near the center while open clusters are found in the disk?
So that goes back to their initial formation mechanisms. So globular clusters have formed early on in the formation of the galaxy, and I'm not as familiar with the precise formation mechanisms. It is possible that they have formed as the gas was still flowing in to assemble the galaxy, or they might have been ejected after the fact. Whereas the open clusters, they're still so very young and they are forming where you have the gas, which is in the midplane of the galaxy.
All right. Are there any more? Or are we? Well, so Marina gave an excellent talk and also kept to time very well, and hence has quite a long. Do you have a question, Jack?
Yeah, can I ask a question?
Of course.
Hi, Marina. I had it. It was such a good question. Darn it, it's gone in my head. No, this is it. So, you made a great comment about how these new kinematic structures are coming on so quickly that it's really hard to keep track of all of them. And that's worrisome a little bit because Gaia is so fast and so furious. So how are you going about it to make sure that, you had some great figures, all of this great clusters, but can you say something about how we're keeping track of all of these and maintaining which ones somebody's published and that somebody else has a piece of it? Theia 362 is a part of Cryos 143, like that kind of thing.
Yeah, no, it's difficult because especially with these extended structures, if you recover one piece of it with clustering and you might associate it with this part, or you recover this different piece of it with clustering and associate with this part, or you have this open cluster that is embedded in the middle of these things and you might want to associate them together, but you would also want to keep the cluster separate for some other reasons. It is really difficult. And sometimes by cross-matching the stars together from these catalogs, we can try to correlate them to one another, but it's not always straightforward. And we're still at the point where we are assembling mechanisms for being able to follow up on them, like we have been able to do with the past with open clusters and global clusters, like in WebDA interface. But this is still a work in progress.
Do you have a website that you can recommend?
Well,
Yeah,
I mean,
okay.
all the source list is public on Bezier,
Mhm.
and I think the same is true for all the other papers, but it is still requires a lot of cross matching.
Okay.
All right. That seems like a good place to stop.